Hello everybody and welcome to this webinar. I hope that you are feeling well and that you are having a great day wherever you are across the globe. Welcome to this webinar about the next generation of solar technologies, where we will tell you all about what we are working on a technology framework within the solar technology part of TNO. And I'm here standing together with my colleagues, Sjoerd Veenstra on the right side of me, who will tell you something about perovskite PV. On my left, you will see Martin Speet, and he will tell you something about sustainability and recycling of solar panels. And last but not least, on my right side as well, is Valerio Zardetto, and he will tell you something about tandem technologies and tandem architectures and why we need them. So, welcome again to this webinar. So, the agenda is as follows for this webinar. First, I will tell you something generic about PV technology trends that we see globally, but also a tiny bit about what we see in the Netherlands. The next part up is Martin Speet about sustainability and recycling and circularity and towards design for recycling. Next up is Sjoerd, who will tell you everything about perovskites and flexible solar modules that can be made with perovskites. And Valerio will tell you something about tandem architectures, which also involve perovskites. And at the end of each of the presentations, we will have time to answer one or two questions. And at the end of the webinar, we will answer the rest of the questions. If there's any questions left, we can answer them by email if it's not possible within the next hour. So if you look at this interactivity of this webinar, you can ask questions by clicking on the orange button if you hover over your screen. This question will end up through some filter in the studio here, and I can ask my colleagues the question that you have for us. This webinar can also be watched over and over again, if you like, afterwards by clicking the same link that is in your email. So let's start, and we will start with the PV technology trends. So if you look at the next generation of solar technologies, of course it's good to see what is already there. If we look at the global development of solar PV installed capacity in the entire world, so that is the amount of solar panels that are deployed and generating electricity for every one of us. Last year we actually surpassed the first milestone of 1 terawatt peak that is installed in the world. And one of the things that made this possible, of course, is technology driven. We have made solar panels better and better over the last years and years. If you look at the Netherlands specifically, there's also the same type of trend ongoing. And actually last year, solar energy counted for about 14%, or could be used for 14% of the generic electricity demand in the Netherlands. And you can see these bars are rising as well, which I think is very, very good news. So the solar capacity is expanding quite a bit, and that is what we need. More renewable energies, and we need to go to a more sustainable future. One of the reasons that is mainly accountable, or where we have all these technology developments pay out in, is the price developments. Over the last 45 years, prices for solar panels have dropped with an amazing 1,000 times. As I said, technology developments have been very, very important to realize this, as well as economy of scale, of course. At TNO, we work on both solar technologies, solar technology development, but also the integration and application of solar energy for our daily lives. And a few examples that I want to show here are applications that are non-standard, such as vertical solar fields, where PV can be combined with agriculture. We can combine solar panels in so-called dual land use, and also in places where there's already structures standing, such as noise barriers, where solar panels can be integrated. And as the final step of integration, in places where sometimes you see it and sometimes you don't see it, such as in a car hood, for example. Well, this is all made possible with different types of technologies. And if you look at the different commercially available technologies, crystalline silicon with 95% dominates the current market in the world. These have, the panels that are made have conversion efficiencies of about 20% on average and can go up to about 24%. But the cell thickness of a crystalline silicon cell, due to its nature, needs to be above 100 micrometer. And the standard is about 160 micrometer. And the panels are typically one size fits all. Well, or maybe one size fits almost all, or maybe nobody anymore, when all the standard fields have been filled. The other small part of the market are called thin film technologies, such as cadmium telluride, which is rather big in the US. There's CIGS, there's organic PV, amorphous silicon, but also, for example, perovskite, who just entered the market, and soon to come technologies such as tandem. And we will tell you more about that in this webinar as well. One of the typical differences between thin film technologies and the standard crystalline silicon technologies is that the amount of material that is needed for these solar panels is a lot less. So we're talking about a few micron instead of more than 100 micron. And that makes a world of a difference. If we look at the current solar energy and solar panels that are produced, solar energy is very much renewable. However, it's not sustainable yet. And if we look at the carbon clock, the clock is ticking. And time is a valuable thing, but our planet Earth is at least as valuable. So if we look at the solar energy, there's a lot of work still to be done. And if we look at the current panel production, and we just surpassed this 1 terawatt peak milestone, this also means that in a few years we will get more and more panels that need to be recycled or that are at their end of life. And currently, 90% of the PV panels that have done their job or are finished at the end of their lifetime, they end up in a landfill. And even though it's possible, we should definitely not do that. And on the other side, we also work on technologies that we call back to the drawing board. So where we can put in as little energy as possible to actually produce these solar technologies. And if you look at the chart in this slide, you can see that there's a minimum amount of energy needed to make crystalline silicon material. And if you look at the timeline there, because there's a lot of pressure to actually produce silicon, you see the energy that is needed to produce it is growing instead of getting smaller. So that is also an item that we definitely need to work on. So at TNO, the main fields that we focus on, or the things that we work on in solar technologies, are to increase the energy yield, so increase the efficiencies of the solar cells and solar panels. We want to increase the stability and the lifetime of the materials. Obviously, we want to decrease the cost, because the cheaper PV panels get, the better deployable they are. We look at sustainability, which has become a very, very important topic, rightfully so. And of course, upscaling of the technology. So what we can do on lab scale also needs to be proven at a larger scale and eventually in the field. In this webinar, 3 of our topics will be highlighted. The first topic will be design for recycling and circularity, so really working on the sustainable aspect of solar panels. The next part will be, well, has been called the new kid on the block, flexible solar modules based on perovskites. And the last will be tandem architectures to boost power conversion efficiency by combining different materials. And with that, the introduction is over. If you have a question, please ask them in the chat. And let's start with the content of what we do at TNO. I would like to give the word to Martin Speet, my colleague, who will tell you about sustainability.
Thank you, Veronique. So you all know the saying, no need to add to the pile. And the pile in this sense is the huge amount of PV panels which we will face soon, so the waste of it. And therefore, the audience today in this webinar, an outlook and an overview towards design for recycling and circularity. So this comprises first information on recycling, then on design for circularity with all its aspects, And then we have an introduction to non-fossil fuel produced closed loop materials. And finally, the traceability of PV panels at end of life. And here to the left, my first takeaway message for you. So by 2050, that's not far from now, there will be enough solar modules installed on Earth to stack a stairway to the moon and back. So this comprises about 30 billion PV modules if you realize a capacity of installed 14 terawatt, and that also will provide us with a global waste volume of 60 million metric tons. That is in equivalent 10 pyramids of Giza in weight. So 14 terawatt will be most likely 30 or even double that. So then you can also double these 60 million metric tons or triple them. And that brings me to recycling, which is done nowadays by dismantling. So the aluminium frame of an existing PV panel is popped off, and the junction box is removed, and so is the copper cable. That goes into a separate recycling stream. The glass plate, the encapsulant, the solar cell, and the backsheet then are crushed and sorted, where the glass is turned into glass cullets used for isolation, and the rest is dumped as filler in concrete or used as grinding material. There is just a better way. That is the delamination. That's one up. And that consists of a mechanical, thermal, and chemical treatment. In the upper left photo, you can see the technology of the hot knife. So the hot knife is a knife that is heated at 300 degrees and cleaves through the panel to take off the glass plate. But as you can see in the photo, it's still contaminated with encapsulant. So it's not residue-free. There's another technology, which is a water jet, that could help here with and be a bit more cleaner. And there is also a low energy, high intensity light pulse technology of 1 millisecond at different wavelengths, which act on the surface of the substrate to delaminate the components layer by layer. We also can consider CO2, supercritical one, as a cleaning method. That leaves us with the solar cells in an encapsulant matrix and the backsheet, and that can be pyrolyzed at a low temperature of 400 to 600 degrees with exclusion of oxygen, and then we would have the solar cell available. So then we can take off the silver alloy of the contact material by nitric acid. But there is an environmentally more sound material for regeneration, and that is methane sulfonic acid, or the MSA treatment. So if we take a further look at the profits which can be made, and then I'm looking at dismantling again. So the aluminum frame delivers us most of the money. The PV glass plate a bit less, because it's still encapsulant residue on it, and it's recasted into window glass rather than turned back into PV glass. So finally, the costs of the recycling are higher than the profits, and this requires a disposal fee. So the wish case is to have access to residue-free materials, and that brings me to the next step, and that is design for circularity. So here are some aspects of design for circularity, as that is not easily adopted at present by the PV industry. And the reason is that it's very hard to change any materials due to the high production volumes and the economy of scale. And there's also product warranties. So there's therefore little incentive to design for easy disassembly and material separation. If we adopt circular materials, that's only possible, we believe, in a step-by-step exchange. So for example, exchanging the standard backsheet with a circular one. And if this material is available, it must be certified and for sure long-term tested. So the good news is there is circular produced backsheet. It's also polymer free, and it could be made from non-fossil fuel production with advanced biocircular or even with CO2 material options for the polymer production. A more trivial case is the glass-glass option. So that's a glass front and a glass rear. So there will be no backsheet needed. And glass is in that sense also a closed loop material. Very important is the monomaterial design to support for easier downstream recycling. Here I have an example of such a monomaterial design. It's in the form of a circular backsheet. It's a co-extruded polyolefin-based backsheet, which means that all the layers are made from one material, and that is polyolefin. So they are modified to fulfill all the requirements of standard standard backsheets, and there is no adhesive in between the layers. So this monomaterial is of thermoplastic nature, and that helps us a lot to recycle, reuse, and it is also therefore a closed loop material. Another interesting approach, what we work on, is the so-called release encapsulant. A release encapsulant has a trigger function. Once this trigger function is activated, then we have access to all the components of the solar panel, and that also residue-free. So to the left, you have there's a photo. You have a picture of a 4-cell module, which consists of front glass and rear glass, so a glass-glass module. And to the photo to the right, you can see what happens when the trigger mechanism is activated. So you see the front and rear side glass plate coming off residue-free. The next photo shows how to retrieve the solar cells. And these modules have been thoroughly tested for long time reliability following the IEC 61215 protocol, damp heat and temperature cycling. The tests were prolonged 3 times instead of the required 1 time, which is 1,000 hours of damp heat and 200 cycle of temperature cycling. The experiments go now all the way up to full-size 60-cell modules comprising this release encapsulant. So if we talk about materials which are recyclable and reusable, then we should talk about the olefins. The olefins come in many ways, like the polyolefin encapsulant, which is cross-linked or non-cross-linked, and also as polyolefin backsheet, as we saw just a minute ago. Here to say is that the world market for PV, this material, the polyolefins, is growing strongly, and they can be made in many forms like oil or natural gas, but also from biomass or carbon capture and conversion into polymers, or from recycled polyolefin material. So if you take a look at the advanced biocircular materials, we can make these polyolefins from sugar, starch, celluloses. It's called the green olefin, but it competes with food. So 3 kilograms of polyethylene would require 83 kilograms of sugarcane. So that's a no-no. And therefore, we better go to check the second generation, which is the non-edible biomass. There is a very interesting plant, which is a castor bean. It's a renewable crop. It grows only in poor soil, and it's not competing with food, and it does not cause any deforestation. So we can go all the way from the bean to polyolefin. Just to finalize, there is a third generation, that's biomass from algae, also to produce polyolefin, but it comes at a very high cost, so this is limited to pharmaceutical applications. If you take a look at the energy balance and the efficiency, it might be a better way to use carbon capture stored and carbon capture utilized CO2 as a chemical feedstock for the polymers. There are 2 major pathways to convert this CO2 into polymers. The first one is electrochemistry. That goes by a catalytic reaction, and the key is ethylene. So it takes this chemical precursor, ethylene or monoethylene glycol, to obtain the polyethylene. There's a second option, that is a biological conversion that's done at ambient temperature and pressure with the help of microbes and bacteria. But if it comes to efficiency, it would be better to choose the first one, the electrochemistry, specifically if it is powered by solar energy. So having talked now about the closed-loop materials and the non-fossil fuel-produced materials, I want to switch now to traceability of PV modules at end of life. So more efficient use of raw materials and a more profitable model for the economics of solar panel recyclate requires that the manufacturer of the original solar panels provide a QR code, a digital badge to all their components in the PV module, and store that data at a digital ledger. That ledger would then allow individual panels to be tracked from creation to circulation. And there is a pilot project already underway, but for PET plastic bottle recycling at BASF. But for sure, the solar community should learn from that exercise and transfer the knowledge towards recycling for solar panels. By the end of the day, the suppliers, the public authorities, the waste collectors, and the retailers and remanufacturing parties and recyclers have access to the information, and the waste collectors can sort solar panels by type and composition. And finally, the conclusions and the outlook. So the PV industry has a strong track record in material reduction and long lifetime, but there will be enormous costs, end-of-user costs for the recycling coming, and that requires novel recycling technologies. So the longevity of PV panels is therefore important to buy us this time for the development of the novel recycling technologies, and design for circularity to retrieve the PV module components residue-free and to increase the reuse potential are beneficial. The PV glass plates, which are turned today, recasted into window glass, should have their dedicated recycling supply chain, just to bring them back as PV glass plates. And the traceability of panel materials by digital ledger and QR code marking would positively add to the business case of recycling of solar panels. And that brings me to my final takeaway message of today. Waste isn't waste until we waste it. And I want to acknowledge two Horizon grants, the projects Pilatus and Triumph, which add enormously to these activities, and also the development of release encapsulant founded by TKI Urban Energy, the Netherlands. And thank you for your attention.
Thank you so much, Martin, for enlightening us with all the sustainability that we still need to solve and that we're working on a lot. There's a call for action in your screen right now for the viewers at home. If you would like to collaborate with TNO on the subject of sustainability for solar technologies, please let us know. Then we also received some questions from you. Thank you very much for that. If there's more questions, please don't hesitate to hover over your screen and put them in the orange question box. The first question to you, Martin, is when do you expect the first PV modules to be 100% designed for recycling? When do you expect those to be in the market?
That's a tough question to answer because that is really up to the industry. So if we consider, for example, the release encapsulant, which could help us a lot already on design for recycling, and also the backsheet, which is made of these polyolefins. So the backsheet is available, basically. So that can be purchased and integrated. The release encapsulant will take a bit longer because it has to be tested more, like the UL test for selling it as a product. But by the end of the day, it is really up to the industry to take it over. And I know it's at the moment pretty hard with the low profits and the low costs of the materials to adapt new ways. But my hope is that we will go more sustainable and reuse more of this material, because we have to. We have to have access to the silicon to reuse that one, because there's a high value in it. We will have not even maybe enough of this silicon, because it requires about 60 million tons just for 30 terawatt. So it's always good to have a backup from recycling sources.
Okay, that's very clear. Thanks for your answer, a detailed answer, Martin. With this answer to this question, I would like to move on to the next speaker of today, which is Sjoerd Veenstra, and he will tell you everything what you want to know about perovskite solar cells.
Okay, thank you, Veronique. Indeed, let's move to flexible solar modules. As the subtitle is the next generation of solar technologies, we can consider here perovskites. And we can also maybe dream a little bit about how the future modules look like. So what if solar cells are produced on a high throughput roll-to-roll line, yielding flexible modules, and which can be integrated everywhere? Now let's see how we can address this question in the next slides. This novel technology then has several requirements, and these are indicated here. And we can start with sustainability, as already explained by Martin. And next is efficiency, stability, reliability, safety, and also scalability and affordability. And in the next slides, I will address efficiency and stability and scalability. Okay, so concerning the next generation solar technologies, let's have a look at this slide, where we see an image that is retrieved from The Economist. And the way I look at this image is that you see a solar field somewhere, and there are some researchers looking at this fascinating crystal structure. And potentially this crystal structure could maybe work together with the silicon solar cells that are out there, or maybe replace them. As this presentation and the next is about perovskite, maybe I give a short introduction to the material. So let me see if I can go. Yes, there we go. The material was first described by the German researcher Gustav Rose, and he named the material after Lev Borovsky. And you see actually the book where he first described some of these materials. And then 1 century later, the material, I should not say material in this case, it's more like the crystal structure, was actually applied in solar cells. And that is indicated here in the first paper that was out in 2009. And since then, the field took up this technology, and there has been quite a tremendous race on improving the efficiency, as I will show later. Now let's have a first look at the crystal structure, the perovskite crystal structure. It's indicated here on the left, and in gray you see the location of halogen atoms. Can be iodine, bromine, chlorine. And then in purple you see the lead or tin 2+ cation. And then in blue, and that is located in the middle, and there you have a large cation that can be of organic nature, or it could also be an element like cesium. Now this group of crystals and group of metal halide perovskites has certain strengths and also concerns, and I try to describe that in the table on the right hand side. Well, first of all, it's based on abundant and cheap materials. So that's very good for cost and also for sustainability. But there's also a concern because, as indicated, the metal can be lead, and that, of course, should not enter the environment. Another aspect is low temperature processing. You can make perovskite solar cells with a low thermal budget. And that differentiates from, let's say, the thermal budget needed for the more, let's say, mainstream technology like silicon. Low temperature processing means that you can make them at low temperature, but possibly the barrier, or let's say the thermal activation barrier to degrade the material could also be a little bit lower. So that's maybe also a concern. Other aspects of these type of perovskite materials for solar cells are defect tolerance, tunable optical properties. That is a very important property. If we look to tandem devices in the next presentation, we can make semi-transparent, translucent and bifacial devices, as I will show on the next slide. It has a low carbon footprint, which is obviously important for renewable energies. And you can apply the perovskite solar cell on different types of carriers. You can apply them on a silicon wafer, for instance, to make a tandem. You can apply it on glass, on PET foil, and on metal. And finally, the material can be recycled. So you can make a perovskite solar cell, you can dissolve it, and you can make again a perovskite solar cell. And these can have very similar efficiencies. On the other hand, if you can, let's say, dissolve the perovskite, there's also a risk that during its life in the field, there could be an issue of leaching towards the environment. And this has to be, of course, prevented. Now, after this overview about the strengths and concerns, let's have a look at some of the solar cells and modules that can be made. Indicated here is that you can make flexible modules, mini modules, you can make rigid mini modules, and you can also tune the optical properties from semi-transparent to opaque. And with that, it shows that it's, I think, widely applicable in all types of integrated applications. And then I go to efficiency, which is, on the next slide. Here it shows the power conversion efficiency over time on the left side. And this is for lab scale produced rigid solar cells. And you see the efficiency increasing from, let's say, 14% to over 26% during the time indicated in the graph. And below that, you see perovskite solar cells made on lab scale on a flexible substrate. And you see that these are also increasing in efficiency and may catch up soon. And then in red is another constraint added to this type of perovskite solar cell. It's flexible, but also upscalable. And you see that here the efficiency is increasing, but also sometimes decreasing, probably indicating that there are not that many data available over time. Then on the right-hand side, you see the power conversion efficiency versus device area of various solar cell technologies. And here you see that for flexible perovskite solar cells, the starting point is at about 24%. But then if we increase the device area, the performance is reduced. And of course, this is a challenge that we would like to take up and make sure that this line becomes more flat, and also to start at a higher efficiency. So that is about scaling up the technology. And in this slide, you see how our approach is towards scaling from lab scale towards sheet to sheet and roll to roll. On lab scale, we make devices on substrate with an area of about 3 by 3 centimeter. And on this substrate, we have 4 devices. And the device active area is approximately 3 by 3 millimeter. If we then move towards sheet-to-sheet processing, we make a similar device structure, but then on a substrate that is much larger. It's about 6 inch. And then we can make the same type of devices, but we can also make mini modules with an active area of 10 by 10 square centimeter. And to make these devices, we use scalable technique, like slot die coating as indicated in the picture below. The next step is then towards roll-to-roll processing. And again, we start with a similar device architecture so that we can compare the performances on the different length scales and process methods. And at the same time, we can also make the mini modules of about 10 by 10 square centimeter. For this, we use a pilot roll-to-roll line at TNO. Now, a few words about stability. That is one slide too fast. Yeah. So about stability, in 2020, we achieved rigid mini modules which passed, let's say, 3 critical stress tests. And after achieving this nice result, we published a press release. And since we see that other groups are also achieving similar results, which is, I think, a fantastic achievement for the whole community. And our ambition is then to move this device stack towards flexible substrates. So that is shown on the next slide. Let's see here. Here we see the stability on flexible sheet-to-sheet processed mini modules. You see that after 200 cycles, you still obtain 98% of the performance. And after 1,000 hour damp heat, we have 92% of the performance left. Then let me go to the next slide. That's the wrong direction. Here. Here we see that we can obtain this stability also on bifacial devices that have a high bifaciality factor of 97%. They can pass thermal cycling, damp heat test, and achieve a power conversion efficiency of 11%. Now we can have a look at a video where we process perovskite on a roll-to-roll line. I hope you see the video starting. Here we see that the substrate, the flexible substrate, in this case an aluminum foil, is entering the roll-to-roll line. It passes through, along the slot die coater that's shown here, where we deposit an ink with the perovskite precursors, and this is entering then the oven. And when it returns from the oven, which you can see here, the perovskite precursor is actually converted in a perovskite layer. You see this dark, nicely light-absorbing layer that is coming back from the oven, from the furnaces, and is then rewinded in the setup. So this we do together with our industrial partner, Hyatt Solar. And the substrate that we use here is also what they use for commercial production of amorphous thin film solar. Now, if we look at the device performances that we can get, on the right-hand side, you see the IV curve that we can measure for the first roll-to-roll process devices. And initial performance was 10.5% for these devices in the first batch. And then we further worked on these type of devices on sheet-to-sheet, and now we can achieve efficiencies of 14.8% together with Hyatt Solar and in collaboration with Delft University and Eindhoven University. Now it's also interesting to further look what can be done with this technology. You can stack 2 perovskite layers on top of each other and make a perovskite tandem device. And this has been done in close collaboration with the Technical University of Eindhoven, where we achieve an efficiency of well above 20%. And that can be pushed further, as indicated on the graph on the right-hand side, where we see that already devices have been obtained with close to 30%. TNO is actually also looking in this technology in the European project Super Tandem with many partners. Another direction that this technology is heading to is being integrated in the mass customization line. This was actually explained in the previous webinar by my colleague Mark Koetsen. And here we use flexible mini modules and we integrate them in a line to make a semi-fabricate that can be integrated on many types of different surfaces for integrated PV technologies. And with that, I come to the concluding slide. So we are working towards solar cells that are produced on a high throughput roll-to-roll line. They yield flexible modules and they can be integrated everywhere. For funding, I would like to acknowledge Hyatt, Perseverance, HyperXL. I would like to acknowledge the province of North Brabant and 2 European projects, so Super Tandem and Pearl, and of course internal financing at TNO. And then, very important, I would like to acknowledge the excellent team that we have to work on these type of technologies. And with that, I would like to finish this presentation. Thank you.
Thank you, Sjoerd, for a very nice overview of all the work that has been done and we are doing at TNO in the field of perovskite PV. There's quite a number of interesting questions, so thank you to the audience for the interesting questions. I will choose one now to answer right now. So Sjoerd, in the graph where the power conversion efficiencies of crystalline silicon and perovskite are plotted, you see that the power conversion efficiency of perovskite go down appreciably when the device area increases. Is this due to a current limitation in the manufacturing process?
Okay, that's a very interesting question, Veronique, and also I'd like to say thank you to the person that asked the question. I'm not sure if it's a limitation of the manufacturing technique. Actually, in the graph you see that there are several lines that have, let's say, a rather similar slope. Let's say in the graph we compare technologies that exist for about decades, let's say, maybe 40, 50, 60 years. And therefore, I think that we can already achieve a similar slope after, only maybe 5 or 10 years of research towards scalable technologies for perovskite solar cells is actually very promising.
Absolutely.
So let's hope that we can make the line more flat and extend the efficiency to, let's say, 20% on large area on flexible substrates.
Thank you for this elaborate answer, Sjoerd. And I think we all believe that it's possible. Thank you. And with that answer of the question, we will switch gears to combining perovskite maybe with crystalline silicon in tandem architectures. So my colleague Valerio will tell you everything about this subject.
Yeah, Veronique, thanks a lot for the introduction and welcome to everyone online. So as mentioned today, I'm going to give you an overview about this tandem concept. And so I will start my presentation with a bit of introduction, so why we need a tandem technology. And I will give you also a little bit of state of the art, so what has been achieved worldwide, mostly on a research level. And then I will jump, let's say, on the effort that TNO is doing about this topic. And again, I think there are 2 sessions, one dedicated to what we call lab-scale tandem architecture. So again, kind of lab-scale devices and a very small area. And the last part will be about, let's say, towards large area devices that might be more relevant for our industrial partners and in general industrial companies. So first question is that why do we need tandem technology? Well, we know that the sun gives us a lot of energy, and let's say this one is represented by the graph on the right. So this is the spectral irradiance all over, let's say, different wavelengths. So we have, let's say, power per meter square per nanometer. And so this amount of power is divided in different regions. So the UV light, the visible light, that is the one that we can see, and the infrared light, that is the one that we cannot see, but we can feel on our skin, for instance. So now if we take, let's say, the best silicon solar cell on the market, and what we can use of this spectrum. So in theory, we can collect and convert up to 33% of the available power. So this is so the rest actually is lost. So this 67%. So this is lost for different reasons, mainly because part of these, let's say, photons and energy is not actually collected, and part because the silicon actually is not converting very well in specific region, especially in the, let's say, the lower wavelength region. So what's the solution there? So the solution there would be, for instance, to make a tandem architecture. And the tandem architecture means actually putting another material which absorbed in a different part of the spectrum on top of the existing technology, for instance, a silicon wafer. So we have two materials that absorb complementary in two different regions. So the top one that absorb more efficiently, let's say, the high photons, so the one on the low wavelength, the low wavelength, and the silicon actually will collect the one on the, let's say, high wavelength or the low energy photons. So with this trick, actually, you can achieve a theoretical efficiency of 45%, and you can massively reduce the total loss. So now the question is that, which top cell we can use? And of course, I think I will agree that perovskite can be one of the most promising candidates to do that. And I think partially, let's say, the reason has been explained by my colleagues. So let's say the perovskite has this characteristic. We can easily tune, let's say, the stoichiometry of this ABX3 structure by changing a little bit the cation and the halides, for instance, and we can change a little bit the absorption edge. So let's say in which part of the spectrum the material will absorb. And the second reason is that when you do this trick, actually you can still get very, very high numbers in terms of power conversion efficiency. And these actually range of what we call band gap are the most suited to be, let's say, complementary with existing technology, commercially available like silicon, or for instance, other thin film technology like CIGS. So how do you construct the tandem architecture? So essentially, worldwide, there are two different, let's say, structures that people are really focusing, what we call 4-terminal and 2-terminal architecture. So in the case of 4-terminal, you simply stack the, let's say, the top cell on top of the bottom cell. This one gives you a lot of freedom how you make the top cell, for instance. And let's say, potentially give you also more high energy yield production. So the disadvantage is that typically you have more layers that you have to make, so there is a little bit more parasitic absorption that can affect the production of the bottom cell. And on a system level, because these two, let's say, devices are electrically independent, means potentially additional cost on your module or system level. On the other side, there is the 2-terminal. So in the case of 2-terminal, what you do is that you build the top cell directly on top of the bottom cell, and the two cells are connected in series through what we call a recombination junction. So here, let's say the advantage is that from a system and module level, potentially you can use the same trick and the same materials that you use for a single junction device. And it's also potentially better for reverse bias tolerance. But I think, let's say, the drawback for this type of architecture is that you might have less freedom how you make your top cell. So you, for instance, produce the perovskite on top of the silicon. And let's say because the two cells are connected in series, I think you have the same current that pass through both of them. So this is fixed. And you might have some, let's say, reduction, for instance, for the energy yield production. So now if you ask which one is the best, I think this is still debatable. And I think this is true also if you look at the next slide. So what has been achieved already, let's say, worldwide in terms of performance of this different configuration. And these graphs are still, let's say, on a research level lab scale devices. So on the left, you have the 4-terminal architecture, and on the right, you have the 2-terminal architecture. So the main point here, the main message is that, let's say, all this configuration, when you combine the perovskite with different bottom cell, whether this is a silicon, this is CIGS, or even another perovskite, I think all of them overcome the performance of the respective single junction devices. So this is extremely positive and proof that the tandem architecture and technology will be definitely the next step in the PV roadmap and the future of product. So let's move to what we do actually in TNO about that. So I will start indeed with few examples of what we can do also on lab scale to be, let's say, more comparable with what is done in literature. So I think you already introduced a few concepts of perovskite, so I don't have to go through. But I think one part is extremely important. So when we think about tandem architecture, you have to, let's say, build up your perovskite device that we call semi-transparent. So compared to a traditional one, where you can use, for instance, an opaque electrode that can be a metal, you have to replace it. And let's say you have to put something that is semi-transparent in order to have that part of the light that is not absorbed by the perovskite pass through and be absorbed by the bottom cell. So what you have to do, you have to engineer in this actually structure to maximize what you can absorb in the visible light, but also you have, and this is mostly on the perovskite absorber, but you also have to maximize what you can pass through, let's say the light that can pass through. So you have to maximize the transparency of all the other layers. And let's say this is a summary of the, let's say, this comparison. So for instance, when we do, let's say that the opaque device, we can get up to 22%. And when we switch to a semi-transparent device, we get in the range of 21%. So this is one of the top-notch results worldwide. And yeah, we wanted to be sure that this is very true. So we also sent to certify to a third party. And with this cell, actually, in the range of 20% after certification, we combine with a silicon heterojunction provided by our partner TU Delft with an initial efficiency of, I think, 24%. And we calculated a 4-terminal power conversion efficiency of 30%. And I think this was the first example for a tandem architecture breaking the milestone of 30%. And it's also kind of psychological barrier for, let's say, the community. So now the 4-terminal architecture can be used also for different type of bottom cell. So in this example, for instance, we combine the same, let's say, device that we just presented with a flexible CIGS with an initial efficiency of 20%. And what you see from, let's say, the top part of this table is that the efficiency jump of 28%. So we have a boost of 8% with respect to the single junction device. So this is remarkable, and this is, I think, the highest efficiency reported up to, I think, the last few months. And let's say because we use a flexible CIGS, for instance, we try to combine also with a flexible perovskite top cell, so the one that Jude mentioned before. So this device was not, let's say, the last generation, so it's not perfectly optimized, but still, let's say, when combined with the same flexible CIGS with 20%, can provide a 4-terminal power conversion efficiency of almost 25%. So again, we get a gain of 5% with respect to use just a single junction device. So we don't limit our research on this 4-terminal architecture. So we also build up several structures with 2-terminal monolith interconnection. And again, here I would just give you an example of what we have done, for instance, on thin film, so CIGS. So we use two different type of cells. So the one that we produce in-house in TNO and something that is commercially available. And I think in all the combination that actually we make and we fabricated, what we see is that we have a significant improvement of the power conversion efficiency from 4% with a commercial product till 10% for instance, for our in-house devices. And let's say what we can claim is that in terms of device performance, we're very, let's say, on the same page of the best research group worldwide. And I think for the flexible device, I think this is the highest performance ever reported, let's say, in literature and with respect to other groups. Okay, so let's move to the last part, so towards large area devices. Of course, as I mentioned before, this is very small devices, and I think one of the mission of TNO actually to upscale this technology and to prove that this technology can be transferred to, let's say, more relevant environment, so industrial environment, and we want to prove it with, let's say, industrial relevant deposition methods. So essentially what you see in this graph is that we want to take the small devices on the left and make, let's say, large area device that you see on the right, that are, of course, much more closer to a final product for an industrial partner. So what we did, let's say we start, of course, with a single junction perovskite that, let's say, is a semi-transparent. So we move from this small scale device with spin coating that we do in our lab. And we use printing technology like slot die, and we deposit on glass. And what we see when we do this transfer, actually, the efficiency of the device remains the same, so in the range of 20%. So let's see, we accomplish the first step. The second step, actually, we build up, let's say, what we call the mini module. So it's, let's say, on, let's say, 100 square centimeter, we have this monolithic interconnection of different cells. And we get an efficiency for our device of 16%. Then again, for a semi-transparent device, is one of the highest worldwide. So now the beauty of this specific, actually, mini module is that this has been designed for tandem application. So for instance, all the other layers have been optimized to be as much as transparent in the infrared region in order to be coupled with commercial product. And this is what actually we demonstrated here, for instance. So we took, let's say, our module, we combined with a silicon heterojunction with 22%, and we calculated a four-terminal efficiency of 25.6%. So we have an increase of 3-4% with respect to the single junction perovskite. And again, this is one, I think, the highest performance on this level of area. And I think if you do the same exercise with another technology, so another bottom cell like silicon, I think we see the same effect. So from 18% from a single junction, we jump to 22%. Again, we see that the tandem architecture can provide much, much more energy per meter square. So I would like to conclude this part, let's say, with partially, let's say, what has been discussed also by Jurt. So, of course, you can make the tandem also building up different perovskite absorbers. So, and this is what we have done, actually, in collaboration with our partners at the Eindhoven universities. And actually, you don't have to stop to making a single tandem, so having two let's say, different absorber, but you can think even further and build up, for instance, what we call a multi-junction. So in this case, we were, I think, one of the first in Europe to demonstrate a high-efficient triple junction device with an efficiency at that time, I think 3 or 4 years ago, of 17%. And this is actually we have done and we achieved because actually we can provide very high transparent TCOs and we can provide highly dense, especially the tin dioxide layers that are really required for this type of technology. And with this one, I think I would like to conclude. And of course, I would like to thank the funding agency to support all this work, Bekijk, Urban Energy, Horizon Project, European Project, and of course, the Ministry of Economy and Affairs and Climate Policy. And you for your kind attention.
Thanks, Valerio, for a nice overview of what we do in the field of tandem technologies, but also what we can expect in the field of tandem technologies. We have some interesting questions from the public. Thank you, a big thank you to the audience for answering your questions. And well, I would like to start with this one. Valerio, do you believe that a 4-terminal configuration will ever be cost competitive against silicon standalone or 2-terminal tandems?
Well, the answer would be yes. I hope so. But I think there are different factors that plays to, let's say, decide whether or not will be cost effective. And it's mostly, I think, indeed, let's say, how much in the end energy you can put, let's say, the device can take out. And if it is, let's say, cost benefit, I think you have to see when you start to scaling up and then see from really like manufacturing production phases.
Yeah. Yeah, a very similar question from another person is, how soon can we then expect these perovskite silicon tandems in the market? Commercially available? What's your expectation? Just
Yeah, let's say we know that there are several initiatives in Europe that are trying to push and towards the commercialization. So yeah, we expect probably next year something from them, maybe end of the next year. This is what I would expect. And of course, yeah, we have to look at China and see what they're going to do.
Well, talking about Europe versus China, I have another interesting question for Martin that we received from the public. Well, it's a question which has two sides. The first is, when do you think we will see large recycling facilities in Europe for solar panels? Does the market first need to saturate to 1 terawatt per year? And or maybe assuming that China dominates the PV manufacturing field over the next 30 years, will there actually be recycling in Europe?
That's a very, very good question. And first of all, let me just recap here something. Actually, recycling is not only done at the end of a panel lifetime, but it's also done already in the industry. So specifically for silicon, there is the so-called off-cut. That means if you have an ingot, so the high-grade silicon, when it is pulled, the mono material, then you have actually a loss of 30% because you have these wings. They are cut off to have a brick to cut the wafers. And they go directly back into a crucible or a quartz tube. And about 85% of the 30% are then recycled. And if you consider 110 kilowatt hours to produce 1 kilo of high-grade silicon, this is really already a big win. And now your question, when this recycling will come. There are incentives, but still on pilot scale. We have, for example, the company Rosie in France. They're working on this pyrolysis, which I already explained in the presentation. They're going for 2,000 ton, 2,000 ton, right? Facility, so it's a pilot line for pyrolysis, and that will bring us more information, I think, on the costs of recycling. For the glass, I believe there will be something going on because the glass is already with low iron content, so you should reuse it as PV glass, as I also mentioned. And I believe that this can be done, but it will be recasted, so it will not be the way that a glass plate will be reused as such, but just remolten, recast it, and then. But when these factories come, yeah, that's a bit looking in the crystal ball. I wish I knew myself, but this is hard to answer.
Yeah, crystal ball and a lot of politics involved probably as well.
Yes, also, yeah.
Yes, which we do not do at TNO. We focus on technology and technology development. Then I have a last question before we round off for Sjoerd. The question is, and I think it's a very interesting question, are perovskites more fragile than silicon ones? And I don't think it's about the fragility from a physical point of view, because you've shown flexible modules, but are they more susceptible for environmental damage or?
Yeah, indeed, very interesting question. Thank you for that. I think the answer is yes. I think that perovskite, let's say by itself, if you make a perovskite solar cell, you have to protect it better against water and oxygen. So indeed, in that sense, they are more fragile. Whether that, let's say, limits their lifetime when they are used as a solar cell or solar panel, let's say, in the field, that is, of course, another question that could follow up. And I would say we don't know yet. The technology is rather young. We see that the efficiencies are increasing, stabilities are increasing also rapidly, but we still need to make a step there. So it's important to do research in this direction in different types of, let's say, type of possible degradation mechanisms. You can think about exposure to oxygen, light, UV, but you can also think about what the impact is of reverse bias, for instance. I think these are very important topics, and that's also topic of future research, for example, in the solar NL project that we hope to start soon.
Yeah, with reverse bias, you are referring to a shadow.
For example, shadow.
Yeah. Well, actually, with the second part of the answer to the question, you answered another question. So I think that was very, very effective. Well, if you have any more questions to the audience, please feel free to still type them in the chat. Everything that we did not cover during this webinar will be answered afterwards by email. So please feel free to still contact us at any time. And with this, I would like to finish up by thanking everyone here in the in the room here with me, Sjoerd, Valerio, and Martin, to be here together and tell the audience about what we do at Solar Technologies at TNO. And thank you for your participation and viewing this webinar. And please, if you would like to do us a favor, fill in the evaluation form. So maybe we can learn for a potential next time. So thanks for now, and hopefully see you soon live somewhere else. Bye.